We have seen the Euler method for the particular case of the evolution in time of the money that you deposit in a bank account. Now we're going to see the general expression for a first-order differential equation in an explicit form. Let's now illustrate the Euler integration method for a general ODE of this explicit first-order form. The goal is to integrate the trajectory in an interval between t0 and t0 plus t in n steps of equal size delta t. We've created here a grid of monitoring times for the trajectory that are equally spaced in the interval. So here we have t0, t1, t2, up to t capital N. We'll denote the values of the trajectory at time tn as fn. The algorithm for the Euler integration method is as follows. At time 0, the trajectory starts at f0. At time tn plus 1, the trajectory can be obtained from the trajectory at time tn by adding this term. This step has to be repeated for n equals 0, 1, 2, up to capital N minus 1. Let's see how the trajectory unfolds. At t0, the trajectory has a value f0. At t1, the value of the trajectory is obtained from f0 plus a evaluated at t0 f0 times delta t. At time t2, f2 is given by the expression f1 plus a evaluated at t1 f1 times delta t up to time t capital N, in which fn is given by fn minus 1 plus a evaluated at tn minus 1 fn minus 1 delta t. We have seen how the Euler method for integration of differential equation works. Let's now program it. This is the code to integrate a trajectory in the Euler integration method. The arguments that the function Euler integration takes are t0, the initial time, f0, the initial value of the trajectory at time t0, a, which is a function that gives us the derivative of f with respect to time, t, which is the length of the integration interval, and n, which is the number of steps that we're going to take in the integration. The output is t, which will be a vector of monitoring times, and f, a vector with the same length as t, with the values of the trajectory at the monitoring times. The first thing we do is to define the size of the integration step, delta t. Then we define the vector of monitoring times. Lin space gives us a regularly spaced grid with n intervals, that means n plus 1 delimiting points, between t0 and t0 plus t. So this will be a row vector of length n plus 1. We initialize the trajectory with the same length as the vector of monitoring times. And finally, here we have the Euler integration method. The first value of the trajectory is f0, and then the value of the trajectory at time tn plus 1 is equal to the value of the trajectory at time tn, and then the derivative evaluated at tn fn times delta t, the integration step.